Okay, so hi everyone. I'm Rohit Kumar Singh, the TE for this course, Nuclear and Particle Physics, uh, being taught by Dr. Paulos from IIT Guwahati. And this is the sixth live session. And this week, on the lecture side at NPTEL, we mainly have some idea of particle detectors that are used in nuclear and particle physics, and then some idea of elementary particles, uh, and then the quark model. So I would like to recap few things and then go through some sample problems, and yeah, we'll see, and you can ask anything if you don't understand, and I'll try to explain. Okay, so let's go. So uh, just to recap everything. So I want to just write down some things that we will use while solving the problems. So mainly, I want to write some things about quarks. So, or rather, elementary particles. So, as you have seen in the lectures, we have uh, two classes of elementary particles called leptons and hadrons. Okay, so I mean these are one with mass. Okay, so in leptons we have electron, muon, and tau, right? So muon and tau are just heavier versions of electron. Okay, they have same -1 charge as electrons, and but they are massive. Like muon is 200 times massive and tau is, I don't know, 1000 or something. I forgot. So yeah, these are leptons, and then in hadrons we have two category. So one is baryon, and one is meson. So so baryons are made up of three quarks, and mesons are made up of two quarks. Okay, so some examples some examples of baryon are proton, neutron, and then there is a lambda particle, then kaons, uh, then you have sigma. There are other higher order resonances. In meson you have pi, okay, yeah, then you have pi, oh sorry, yeah, okay, it's fine. Wait. Kaon is a meson. Proton, neutron, lambda, and let's say what else you have? Sigma you have, and then there is a called cascade. So these are baryons, and pions you have. Sorry, in mesons you have WZ bosons and pions. These are mesons. Okay. Wait. No. What am I doing?
So W and
Yeah,
Z are both.
they are bosons. Sorry, they are not meson. They are weak charge, weak interaction carriers. Sorry, I meant to write kaon. Okay, so pion kaons are most common mesons, and we have other mesons also. Okay, and then we have the charge carriers. Or those who which mediate the interaction between these particles. Okay, so we have photons which mediate the electromagnetic interaction. Then we have W and G bosons which mediate the weak interaction, and then we have gluons which mediates the strong interaction. Okay, so I'm not writing anything about gravitational interaction here, because in standard model of particle physics we don't take into account the gravitational forces, because its magnitude is very low and we don't know about what happens at very low, I mean very small distances to gravity. So we don't have a theory of quantum gravity yet, which has been verified or tested. So yeah, so this is the standard model of particles that we have. I mean these particles are there. Oh, and then we have neutrino also. So electrons have so these also come in lepton category. So electron neutrino, then muon neutrino and tau neutrino. Okay, and one last thing that you have is something called Higgs boson. So which gives mass to all the elementary particles. So those who are massive, because they interact with Higgs, and those who are massless, they don't interact with Higgs. So interaction with Higgs provide mass to all the particles. Okay. So yeah, this is the standard model of particle physics. Now so leptons are fundamental particles. Okay, and hadrons are hadrons are hadrons are made up of this thing called quarks. So quarks and leptons, they are basically the fundamental particles. So we have 6 type of quarks. So up quark, which has charge plus 2/3, and its mass is something 2.3 MeV. Then we have down quark, charge is -1/3, mass is 4.8 MeV. Then we have charm quark, again 2/3 charge, but its mass is 1275 MeV. So these mass are not really accurate. I mean, we cannot say that we are 100% sure that its mass is what we are writing. So these are experimentally what we have observed, and standard model also gives these masses, but it has some uncertainty. So just to keep in mind, because we cannot observe free quarks except this one. So the top quark, its mass is known precisely. So anyone know why top quark mass is precisely measured?
So is it because it's extremely heavy, so it's easier to measure?
uh, Easier to measure means what?
It's extremely heavy, right?
Mm-hmm.
So it's easier to measure it because its interactions are going to be more prominent.
Mm, yeah, I mean that is not true. Okay, we will. I think I have a problem on this, so we will discuss this. But one thing that I would like to discuss here is, you see, the up and down quark, their mass is very low, right? So proton, you know that it is made up of UUD quarks, right? If you add up these masses, so 2.3 plus 2.3 plus 4.8, it will give you 4.6 plus 4.6 plus 4.8, so it will be 10.4, right?
So 9.4.
Oh, sorry. Yeah. 9.4. Okay, yeah, 9.4. But we know that the proton's mass is 938 MeV, right? So, so then why, like, where the other mass? Like like the quarks accounts for only 1% of mass, right? So where does the 99% of mass come from? Anyone know?
So the energy of the things that force that is holding them together.
Mm, yeah, I mean that is uh, a layman answer, but yeah, that is,
Binding energy of the quarks.
yeah, something like this. So so you know that the proton consists of these three quarks, and the quarks interact through gluons, right? The strong uh, interaction particles. And so inside a proton there is a, sea of gluons, and there is a theory called quark confinement. So this confinement basically, adds up to the energy. So yeah, it's like a binding energy kind of thing. So like in the nucleus, the total energy, the total energy of a nucleus is just addition of number mass of the protons and neutrons, and I mean mass of the nucleus is equal to the mass of protons and neutrons, and then the binding energy, right? So similarly, you have, in the inside the protons, uh, there is a confinement of quarks, and due to that, uh, it adds up to the mass of the proton. So that means, and you know that our universe is basically made up of these protons and neutrons, right? Most of, so we can say that the 99% of the mass of our universe comes from this confinement, right? This only 1% comes from the Higgs boson. So this 1% is the mass of quarks, and which is there because of the Higgs boson. So only 1% of the universe mass comes from Higgs boson. Other 99% comes from the confinement of the quarks. So it's an interesting thing to remember. You can read about it more. So there is a bag model of nucleon, uh, which explain better what I'm trying to say. Yeah, but these are for later studies. So yeah, let's dive into some questions, and I will explain other things along. Okay, so anyone want to ask anything here? If not, then let's move. So, first problem. So you have to select the correct statements out of these. So this is based on the particle detectors. So first option is that a drift chamber is used for measuring the position of particles. So what do you think? Is it correct? Okay, let me read all the options, then I will ask which one you see correct. Then the second option is Cherenkov detector is based on the ionization of the medium. Then we have proportional counter is based on ionization of the medium. And then multi-wire proportional chamber makes better position measurement compared to single anode proportional chamber. So these are the options. So uh, anyone want to answer?
So option 2 and 4.
So option 2 and 4 you think is correct, right?
Yes, sir.
Anyone else want to guess? Priyanka, Binod? Hello guys, can you hear me? See, this session is to interact with each other. Like you can ask question, I can ask, and you can answer. So otherwise, I mean, it's not a lecture. So that's why it's going live, right? So yeah, please try to interact. Okay, so Adnan, why do you think second is true and fourth is true?
So second one, because the basic principle of the Cherenkov detector is from the radiation that is released when the particle travels faster than the speed of light in that medium, right?
Yeah,
So an ionization sort of thing occurs, and in
ionization. So ionization of what?
the medium particles.
Mm, okay. So yeah, I mean what you're saying about Cherenkov radiation is true, but there is no ionization of the medium because in the Cherenkov detector is made up of photomultiplier tubes, right? Which are just photo detectors. So they convert light signals into electrical signals. So uh, there are no ions. I mean, there are no gas that in the photomultiplier tubes. So
But radiation is released, right? So that
yeah,
means something.
radiation is released, but uh, what you measure is the angle, right? There is a formula cos theta equal to. So you measure through the radiation, you measure the cone of the shock waves, right? Which gives you the idea about the velocity of the passing particles, and then actually you can calculate the mass of the particle. So so yeah, ionization doesn't happen because of the radiation. The radiation is just detected by these photomultiplier tubes. Ionization happens in this proportional counter or drift chamber. These works on the ionization principle of the medium. So when you have a chamber like this, radiation is passing. It ionizes the surrounding gas, and which I mean it knocks out the electrons, so you have positively charged ions and electrons which you can apply electric field, and they will drift towards cathode and anode, and then you get an idea about the passing charged particles.
So, but if the radiation is being released, that means something is being ejected outwards, right?
Yeah. So,
So, so that rate.
I mean for the, yeah, but you can use scintillator, like so. I mean basically, the Cherenkov detector consists of this SIPMs, the silicon photomultiplier tubes, and so yeah, the ionization. I don't think ionization is a right word there.
So, but if a particle goes through the medium faster than the speed of light in that medium,
Uh-huh.
so the radiation is produced. So that means something is coming out of the medium, right? But uh, the particle itself is not radiating anything. It's not releasing anything. So
No, no,
the
no.
only thing
The
that is,
the radiation comes from the charged particle, right?
or the particle that is traveling is the one that is radiated.
Yeah. Cherenkov, you can read about this Cherenkov radiation, how it happens. So it is a particle that is radiating, not the medium. Because it is because of the medium. Because unless you have a medium, the you cannot travel greater than speed of light, right? But it is the medium. It is the particle which is giving out the radiation, charged particle. But it is a very special type of radiation. Uh, it is a shock wave of light, sort of like when uh, you know jet passes at greater than a high speed of sound in the sky. They leave behind shock waves. You can see a trail of gas, or vapors. So like this.
Yes, yes. So that the vapors or the gases are composed of the medium particles, right?
mm, in this case, no.
I mean, because if the particle which we are passing through the medium is ejecting the radiation,
Mm-hmm.
that means that something is happening to it physically. Something is happening to it physically.
Yeah.
So we'll lose the particle's original information, right? Because now it started radiating, so it's releasing something. But
Mm-hmm.
that's not what is happening. So I thought the medium is getting ionized because of the particle's velocity. The medium gets ionized, and the thing that comes out is the radiation we observe.
No, 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 no. Yeah, yeah. The analogy is not really correct with the jets. But yeah, here, no, here the particle radiates, as far as I know. But I can check it, uh, because you see, these detectors, the Cherenkov radiation. I mean, yeah, they slow down the particles eventually. Uh, when the particle enters the medium, it travels greater than speed of light. But yeah, obviously it will lose its energy. So it's kinetic energy which is getting converted into the radiation that is emitting. But yeah, I'll have to check it. Maybe what you are saying is also true. So yeah, I will check. But anyway, if it's a solid state material, then ionization is not the right word to say anything. Okay. So yeah, right now I will say this is wrong. Why not? Why not the first option? Why did you not choose the first option? Did
Yes, sir. The first option also, I think, is correct.
Yeah, right. Because drift chambers are used to measure precisely the position of particles, right? You know how drift chambers work. So there are multiple anodes which are placed inside the drift chamber, and when a charged particle passes, so there are other scintillators which gives you the time at which the charged particle has passed through the drift chamber. So you know the time of you know uh, primary interaction with the medium, and then suppose it takes some time to reach your anode. Okay, so then you have the T naught. So suppose this is the T naught at which it knocks out an electron, and then the ion, or yeah, and then the electron goes to the anode, and you know that you note the time T. So you have the time, sorry, so you know the time which it took to travel this medium, and also you can calculate the drift velocity, which depends only on the constant electric field, right? So you have time, you have velocity, so you can calculate the distance, right? The distance traveled. So you will precisely know from where, like how far the interaction happened. So you can reconstruct the track of the charged particle. So I mean these are done in in algorithms. So this is what uh, this is how we design the software of detectors. So there are reconstruction algorithms which does these things, but the basic principle is the same. So yeah, drift chamber is used to measure the position of particles, and then the proportional counter is based on this one is also true, right? Proportional counter is also like drift chamber is a kind of a sophisticated proportional counter, right? In proportional counter you have just one anode, and uh, the charged particle ionizes the medium and you get a signal. I mean, when you apply potential difference. And then the multi-wire proportional counter makes better position measurement compared to single anode. Yeah, because here you have multiple wires, so uh, you can, I mean, you can see which wire picked up the signal. Then you will have some idea of where the charged particle has passed. So these are these were used in old times. Right now no one uses these things because we have very sophisticated detectors now. There are silicon detectors, silicon strip pixels, and then the drift chamber is also used in some detectors, like Alice uses it, and but in CMS we have mainly solid state detectors. But the basic idea is same. They now caught the electrons from the lattice, and you have electron hole pairs which then you apply electric field and they move to respective uh, anode or cathode, and then that I mean you get a signal in the readout electronics. Okay, so yeah, these three options are correct. Second one is wrong for now, but yeah, maybe I'll look into more details of this Cherenkov radiation, and we can discuss next time. Okay, so let's move to the second problem then. So yeah, this is a very trivial question. So UUD are the constituent of which of the following hadrons? Anyone?
Proton.
Yeah, it's proton, right? But what about lambda? Do you know its quark content? I mean, you can look up to it, but yeah, yeah, proton is true. These, so one thing to notice is that these are, heavier baryons. Proton and neutron, they are light baryons because they are made up of light quarks. Okay, and whenever you go from proton neutron to higher order resonances, heavier particles, you will either have, either a strange quark or charm quark inside the, I mean, as a quark constituent. So just to keep in mind. So sorry, these are not right. Okay, so next problem. So you have to choose the correct statement or statements. So first is one can detect free quarks. Then second one is gluons are massive. Third one is neutrino can interact with proton to produce neutron and electron. Then proton is its own antiparticle.
So D, option D.
Option
D, the last one.
only this. Others? What about others?
So free quarks are not possible. Gluons are not massive. They almost have a mass
Free
of 0.
quarks are not possible. Yeah. Gluons are massless, right?
Yeah, they're almost massless.
Okay. Yeah, that is true. So,
For option C, the proton can decay into neutron plus electron plus a neutrino.
mm-hmm.
But so it's on the RHS of that reaction. So it's not that the neutrino can interact with the proton, right?
So, so this reaction, right?
Yes, sir. Sorry, sir. Positron, not here.
So first thing, if you notice, uh, I mean this reaction only happens inside a nucleus, right? It cannot happen, I mean, for a free proton. So protons are very stable. Why is that? Why it cannot occur for a free proton? I mean, outside the nucleus.
Sir, not enough energy for the breaking.
Mm-hmm. That is not true, because proton has mass 938 MeV and neutron has.
Neutron is heavier. Okay.
Yeah. So energetically it's not possible. If you find the Q value, it will be negative. But inside the nucleus, you can have, like, there are other interactions there, right? So energy balances, like the nucleus can recoil, or it can take energy from recoil or something. So it happens inside the nucleus, but it cannot happen for a free proton. And so this is what we write. But how does this, this is beta decay basically, right? So this beta decay, how does this happen? Do you know? Like in particle physics terms, so you have a proton, you have UUD quark, and you get UDD quark, right? This is proton, this is neutron. So at the quark level, one up quark is getting converted to down quark, right? And you also get then electron and antineutrino is emitted.
Also, positron, right? Positron and
Sorry,
neutron.
yeah. In this case, positron. And this interaction happens through, you know, W plus boson, I guess. Yeah. So I mean, yeah, this statement is not totally correct, because if it was like W boson can interact with proton to produce neutron and electron, then it would have been true. But yeah, I don't think we can take it correct, because neutrino is like produced as a consequence of interaction with, W boson. So yeah, okay, it's fine. Photon is its own antiparticle. Okay, is it fine? Okay, so let's go to the next question. So the next question is, yeah, this was the problem I told you about. So the top quark does not usually form bond states like other quarks, because, so this is the reason why we can have, this is the reason we have the, precise mass of top quark, because it does not form bond states. And the question is why it cannot form bond states like quarks.
Option one.
Every quark form bond. Option.
Option one, right? So the top part decays quickly.
Yeah, they decay quickly. Now, why they decay quickly? You said something about its mass, right? Because, I mean,
Oh, is
the
it
reason
the
was,
mass?
the reason you gave was wrong, but I mean, you are going in right direction, because it is very massive, so that has something to do why it decay very fast. So, do you know why? What is the principle?
Is it too massive for weak forces for it to hold together?
Which, too massive for what?
For the forces to hold together, the gluon force.
No, that is not true. So I mean, it doesn't even have time to, like for a gluon to interact with, like, from like gluon field to interact with other quarks. It just when it get formed, it just decays. Okay, it doesn't have time, and we measure its mass through, its decayed products. So the reason is, because it is very massive. So there is a very, fundamental principle of quantum mechanics, this the uncertainty principle, but with energy and time. Do you know this?
Yes, sir. Like it's a variation of Heisenberg's uncertainty
Yeah,
principle.
yeah, yeah. So this delta E can, I mean, it can be written in terms of, because here the rest mass energy, because if top quark is formed at rest, then you only have the rest mass energy. So delta mc square delta. So since it is, it is very massive, so
delta t is very less
Yeah,
because this thing is
yeah,
massive.
yeah. I mean, when 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 you will plot something like this, so there is a thing called mass invariant mass invariant. So this we use in particle physics experiments. So this is how the Higgs was discovered. So you will see that it has a very sharp. Oh, sorry. What am I doing? It has a very it has a very wide peak like this. Okay, because it has a very high method. When it gets formed, it's uh, it's so massive that because of this uncertainty principle, the time it takes to decay is very like it is there for a very less amount of time. Okay, so that is the basic reason. But I mean, this is only this is only true for the first order estimations. You can find variation of this uncertainty principle in the quantum field theory, which will explain more correctly why it happens. But yeah, something to do with this. Okay, so then next problem. So you have to select the correct statements out of this. So frictional force is not a fundamental force. Friction force can be attributed to electromagnetic interaction. Then friction force is due to gravitational interaction. And the last one is a book placed on a table does not fall through the table due to the normal force. The origin of the normal force is electromagnetic interaction. So which is the true statement?
So the last one is true. Uh,
Okay.
the third one just seems kind of off because if there is no gravitational interaction, but if I'm putting, for example, if I do an experiment in vacuum and there's no
Hmm.
gravity over there, but I push if we take the same example as table and the book, if I push the book
Mm-hmm.
and the table close together, the frictional force will still be present.
Yeah.
Gravity is not required.
Yeah. Obviously.
But on Earth, because of gravity, that those two are getting pushed together. So, uh,
No.
it,
I mean, you can forcefully push two things together. The friction will be there, right? Friction
yeah,
has
yeah,
nothing to do
but
with
on Earth,
gravity.
the gravity is doing that for us, right?
Yeah. I mean, if you don't have gravity, you can use your force of your hands to rub two things together, but the
Yes,
friction will be there, right?
yeah.
Friction.
So for the third option to be right, it needs to be in a proper frame, lab frame.
Yeah, 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 that is true. But
So the
yeah, it is not. But here it want to say like frictional. The origin of frictional force is gravitational, which is wrong, right?
yeah, for that then it's wrong, and the second and first one are also true.
Also true.
Yeah.
Yeah, it is not a fundamental force and can be attributed to electromagnetic interaction. So frictional force is just electromagnetic interaction at the macro level, micro level, because it is just the interaction between electrons of one object to the other one. So I mean atoms of the other one. So at micro level, it's just electromagnetic interaction. Okay. So then let's move. So it's again a very simple question. So we have to match the interaction type of interaction with the carrier. of those interactions. So electromagnetic interaction, this goes to photon. Strong nuclear interaction, gluon. I mean, this is just trivial, right? Weak nuclear interaction, G boson, gravitational interaction, mass. So why I don't know why the mass is given here, because gravitational, I mean, these are these are interaction carriers, these are mediators, right? Of
Gravity doesn't have a mediator yet, so
Yeah, I mean, they could have wrote graviton or something. It's
grav.
a
Yeah. But graviton is still theoretical, right? We
Yeah,
haven't.
it's theoretical. Yeah, I mean, theoretically it is there in many theories. Like you can even in quantum field theory, you can you can use graviton with +2 charge, and there are many calculation like this. You can obtain the basically the Newton's formula for gravity uh, using the graviton inside the quantum field theory. There are some interesting things, but yeah, it is still it is hypothetical.
Also, it feels like it's just for convenience because the other three fundamental forces have a mediator, so gravity also needs to have one.
yeah. I mean, if if the quantum gravity theories are right and we can test it, then yeah, we'll see. So yeah, this is fine. Then okay, so it's a simple problem. So we have to find the odd one particle out. Okay. So
Last
which
one, sir. Kaon.
why?
So it's a meson, no? The
Yeah.
other two are baryons, and the last one is a meson.
Yeah. Okay. Yeah. True. That was fast. So let me ask once again. So Priyanka, are you following through, or you can also answer some of these questions? Can you hear me? I think she joined and then slept or something. Okay, no problem. Okay, so what about these four? Uh, can you tell which one is the odd? It is not that easy, right? No?
So again, should it be the proton because it does not have multiple this thing
What?
states?
What? Multiple what?
Multiple. I don't know the word, but in layman terms, like multiple states.
No, no. These are all baryons, right?
These are all baryons, but sigma has sigma naught and sigma plus,
Mm-hmm.
and
Yeah,
the
then I would then the problem would have been, one sigma would have been given and one other baryon would have been given. So I don't think that is the reason. I mean, yeah, you are right that proton is the true correct answer, but it is not the reason what you are saying. So think about it. Like, what there is something common in these three.
or do they have the strange quark? All three of
Yep.
them.
So
Okay.
that's what I was wanted to tell you. So these are all heavy baryons and they all have strange quarks. So like the sigma 0 has UDS quark content here, UUD. The cascade 0 has two strange quarks, and then this cascade plus it has one charm and one strange. So yeah, strange is common in all the three, but in proton you don't have any strange quark. So that's why it's odd one out. Okay. And what you were saying is you meant to say it has, these all have isospin states, right?
Yes, 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 sir. Yes,
Yeah,
sir.
yeah.
Isospin states. Yes.
Yeah, but proton and neutron makes up the isospin states, right?
Also, we can say that they're basic fundamentally this in terms of isos spin they are same
Yeah, yeah, yeah.
same particles.
No, I mean, isospin is what differs them in term, because uh, strong force, you
Oh no,
cannot.
no. I the spin sorry the spin family they both are spin half family, right?
Yeah, 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 yeah. There, I is half, and then I three is plus half for this and minus half for this. So that's how we classify them. Okay, and yeah. Then let's go to the next problem. So then here you have to find out the odd one out considering their isospin and I3 values. So now tell me which one is the odd.
So automatically, like I would assume it's pion because
Which
uh,
one? Pion?
yeah the second one.
Why? Why?
So because like it is a meson and the other oh no
Oh,
wait
the
wait
kaon is also there.
okay, kaon is also there wait. Uh,
So let's write the isospin. So it's I is 1, I3 is 0. Here also I is 1, I3 is 0. For lambda 0, I think I is 0, right? Lambda is singlet.
yes sir.
I3 is also 0, and then for k on, we have I is plus half, and third component is plus half, right? So for me, I think this one is odd.
So K0 is also half.
Yeah, yeah. K on will just, they come into, yeah.
Yes, sir. K0 is also I3 is I3 is minus half for K0.
K0 I3 is minus half or plus half? I'm not
Uh,
sure. Yeah, yeah, yeah. Maybe it's minus half.
so then the correct option is K on.
Mm-hmm. Yeah, yeah. K on is the correct. Okay. So then let's go to the last problem that we have for today. So which of the following has strangeness quantum number s is equal to plus 1? So what do you think? By the way, like looking at these particles, can you write the quark content without looking up? Like, can you guess the quark content? If you have some minimum information, like you know that the kaon have kaon have one strange quark, because yeah, these are strange baryons, right? So can you guess the quark content?
So like you can guess that they have a strange quark, but you don't know if it's a strange
Yeah,
or
but we
anti-strange.
can do that if, like, based on the charge we can do that. Let's see. So it is k plus, okay? So you have to get charge is equal to plus 1, okay? And you know that the strange quark has a charge of,
Zero.
no, strange quark has minus 1 by 3 charge, right?
Oh yeah, yeah.
Okay, so q of strange quark is minus 1 by 3. Now to get plus 1 charge, what do you need? And you know these are mesons, so they are made up of two quarks only, right? So what would you put in order to get a plus 1 charge?
So you can put a U.
Mhm. But wait, whatever you will put, you will not get, I mean, whatever quark you will put here, you
You
will
won't
never
get
get one. So
multiple.
that means the strange quark comes in this as a antiparticle, anti-string, right? And which has the charge equal to plus 1 by 3, and then you
Then
can
you put a U and then
u,
2 by
yeah,
3,
yeah,
cancel 1.
then only u can be there. So quark content will be u s bar, right? Similarly, here you have q equal to 0, and then you have a strange quark. So what do you need here now?
Plus 1 by 3 UT.
Plus 1 by 3. So which quark has plus 1 by 3? No one has,
D.
right? Yeah.
No.
So, but down quark has minus 1 by 3. So you can take d bar and then you get plus 1 by 3. So its quark content should be this, right? Similarly, then for minus 1, again strange quark, minus 1 by 3.
U bar.
You need a u bar, right? So then it will be u bar s, right? And then for the lambda, then it gets tricky because lambda has 0 charge, right? And it is a baryon, and also lambda has a string, lambda is a strange baryon, so it has one strange quark, and so you get minus 1 by 3. Now you have to go to 0, right?
So we can have a U,
You can
and then
have
we can have a D
u,
bar.
and then you can, why
Oh,
d bar?
D,
Just
D,
you can have
D,
d,
D.
right?
Yeah, D, yeah.
Yeah. So yeah, this is the string. So then a strangeness, what is the strangeness? So for one strange quark you get a strangeness minus 1, right? So here also minus 1, here also minus 1, here also minus 1. Now here you have s bar, so its strangeness is
Plus.
plus 1. So k plus is true. So yeah, this is little trick you can use.
So you don't always have to use the isospin that the quark model lecture in that sir had taught some method
Method
for figuring out quark content. Like you use the isospin.
yeah, I mean you can use isospin also. Sometimes maybe isospin can help in some cases. Because you have isospin, the isospin for each quarks, right? Quarks also have isospin doublet, so u and d quarks fall under the half isospin doublet, and then you get the doublet for the anti quarks. So yeah, these can also be used sometime, but yeah.
But this charge method is more easier.
Yeah, this is. But here you will have to know whether a charm is there, or whether sorry, where a strangeness is there, or charm quark is there. Then that you to know those things, you have to know which kind of baryon you are looking at. It is a higher mass baryon, so higher resonances. So it's more probable that the higher resonances will contain strange and charm. Some also bottom quark will also be there. Some cases like ds, d plus, d minus. So yeah, but these are, I think, I mean, these are not much useful things because anyway, like it is good to know these informations, but in any of the practical applications we don't have to remember everything. Like, these things are informative, these you can look up these things anywhere, right? You have to understand the concepts, why behind this, like what is going on. And I don't think this week's lecture had many conceptual things, they are mainly informative, right? Just listing
Yes,
out
sir.
things. And yeah, so also I don't like this, this idea of uh, doing approximate things. But yeah, like in the lectures, I saw the professor using, writing some concepts of group theory, like writing SU3 and telling about SU3 groups. And then, but these things you will not understand unless you go deep into the theory, right?
Yes, sir. Even I didn't really clearly understand. Like,
Yeah, 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 I mean, yeah. So yeah, unless you take some advanced courses, you will not fully understand what's going on. But yeah, I mean, for having some idea, it is fine. So yeah, I don't have any more questions today. So, do you want to discuss anything else, or you, also you want to take more tips? Do you have any question regarding your career options? You can ask.
yes, sir. But I mean, like, well, I am from an engineering background, right? So,
Yeah, yeah. So yeah, that's what I'm saying. So for you, I mean, it will be more convenient to enter the experimental high energy physics, because yeah, there you can also learn about hardware, do something in hardware also, computational. Because I mean, the analysis that we do is mainly computational, so one needs to know more computation. But yeah, like physics will be very less, like 20%, 10-20% of physics you need to know, or physics discussion will be very less. But motivation is always the physics, that's what we are doing. But yeah, there are many technical aspects also involved in this field. But if you really want to like learn, I mean, go deep into the theory, then yeah, you will have to struggle a little. Because
uh,
yeah, this is the reality. See, there are not much position opening. You can see, like how many PhDs are working, I mean how many professors are working. Like in IIT Madras, there is no one in particle physics theory right now. One professor joined, I think, this year. uh, but you see, there
so
are many experimental physicists.
outside, like in abroad countries, there are many theoretical institutes purely for. Even in India, TIFR and all those are mostly theoretical institutes, right?
Yeah, yeah, no. TFR is not only theoretical institute. Like in
No,
T.
no, not only theoretical, but they have a heavy emphasis on fundamental research.
Yeah, so fundamental research doesn't mean only theory. I mean, I have been to TIFR, and they right now they focus mainly on experiments. I mean, they do experiments to test the fundamental theories. That is true. But yeah, there are good theorists there, but I don't know if they will. I mean, yeah, you can. That's what I'm saying. You can find a position, but yeah, you will have to struggle. It
Yes, sir.
depends on your interest. Like,
Yes, sir. No, the theoretical is more interesting than
yeah,
experiment
obviously
because
it is. Obviously, it is interesting. Um, it's okay, but yeah, think about it. how.
Yes, sir. Yes.
Mhm.
So, and what about like projects, for example, if
Yeah, I'll say you must do some projects before entering PhD. Okay.
so, sir, for so, do you have any like recommendations, like what type of projects I can look into?
I mean, so you want to if you want to do theory in your PhD, you should contact some theorists for a project. Then I mean, you will get an idea what research is all about. See, studying a theory is very different than researching on it, right?
Yes, sir.
So yeah, you should try, you should I mean, you must do a project before entering PhD. Otherwise you will regret if you don't like the way the research works later. So then you will have no way to go. So it's better to, first get some idea of how research works and whether you like it or not. So
So, how about writing like review papers and research papers?
uh-huh.
Are those because I in my first year of engineering I wrote a review paper,
Mm-hmm.
and then right now as well I'm thinking of contacting one of my university professors to write another review paper more towards theoretical physics.
Okay. Yeah,
So
that is fine. These are good ways. But again, I'm saying that writing a review paper is very different than doing something. Doing a new, working on a new theory or new project or doing something.
so how do I enter into I mean under some theorist who is working on
Just
new
yeah, you
projects?
have to just mail them, right? You have to just mail some professors asking them that you want to do some project under them, and that is not. But yeah, for that I think you should do a masters in physics first, right? Otherwise, I mean, you have to know basic quantum field theory and some mathematical theories. You need to know, right? Otherwise, doing a project, I don't know how much it will be helpful.
Yes, sir. So that's why I thought maybe if I write a review paper for in the field that I'm interested in, like when I do approach any of the professors, I can tell them ki I have somewhat of an idea because again I'm from an engineering background, so they might be a little hesitant to
Yeah,
take
yeah,
me.
yeah. No, no, yeah. That is a good idea. Yeah, yeah. That is fine. Yeah, you can try that.
So those things. Along with that, I have to like also look into preparing for any of the entrances exams for MSc.
Yeah, yeah. That is true. Yeah. Yeah, those are easy. I mean, you can try for jam or something.
Yes, sir. Jam. I was yeah jam. Like I'm thinking of writing it after I complete my engineering.
Yeah, yeah,
So those things. Even Jest is there, and even for TIFR, there's one, right?
yeah. Yeah, TFR takes its own exam, and through Jest also it takes. So yeah, these things you can consider, obviously. Okay, so yeah, all the best, and if you want to ask anything about experimental energy physics, then I can tell you more because I am working in that.
Yeah.
Uh, so yeah, if some questions comes into your mind, maybe you can discuss next time.
Done, sir. Done, sir.
Yeah,
So could you give me like your mail or something if I had anything to ask?
yeah, yeah. Okay, I'm writing my mail ID in the chat.
Yes, sir.
Right. Okay, so this is my mail ID. This is my institute mail ID, so you can just
Yes, sir. Good, sir.
Okay.
Are you working on any projects currently?
Yeah. So I'm doing the PhD, so we have to work on something, right?
Oh, okay, okay. So, what does your work like? Like, so you just collect data from CERN and you make interpretations of that, or?
Yeah, something like this. We, so yeah, the data comes from CERN, from LHC, and we are mainly interested in this heavy ion collisions. Okay, lead. So lead colliding with lead. So last time I discussed something about it, right? Uh,
Yes, sir.
yeah. Uh, so then when the collision happens, because they are colliding at such high energy, 5 TeV, center of mass energy. So there is a so what happens is this proton neutrons that are inside the lead nuclei, they get melted, okay, and quarks quarks basically comes out of them, like quarks and gluons. They are released from the protons and neutrons uh, for some time, okay, and they form a soup kind of thing, hot soup of plasma. We call it quark gluon plasma. Have you heard about it?
Yes, sir. Quark gluon plus. I might have
Mm-hmm.
heard of it.
Yeah, so yeah, I mean, it's still it's still the quarks are not free in the true sense. Like you will say that we know that quarks cannot be free, so how come quarks are free now? Can we detect them? But quarks, I mean, they are not truly free because they are still confined within a volume of the nucleus. Okay, so the color confinement is still there, but because of the high energy, I mean, that we have provided, it, the boundary of protons and neutrons, that has disappeared basically, okay.
Mm.
So that state is formed, and it's a very exotic state. And then those quarks and gluons, they again, I mean, the plasma basically cool down and quickly, and then hadronizes, I mean, they again uh, recombines into various particles like protons, pions, and things like that.
So,
So
sir, the reason for this thing is to study the an isolated quark property, like almost isolated quark property.
no, 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 not about quarks. The I mean, the basic motivation for this is to study this quark gluon plasma only. Okay, how it behaves, and because we know that in the beginning of our universe there was such kind of plasma existed, right?
Yes, sir.
So that's what the main motivation is. But I mean, there are many rich physics that we can study through these kind of experiment. Uh, so yeah, then we detect those particles. So just to give you an idea, we one lead nuclei gives us about 10,000 of particles in the detector. Okay, and through from those particles we trace back to what happened in the when the lead nuclei collided, and I mean, we try to find something about coagulant plasma, its properties, and all that. So it's a very interesting field also, but yeah.
It can also give you the nature of hadronization, right?
Yeah,
I
yeah,
mean,
many things. Yeah, obviously, particle production and
so also like could it help figure out why there are more particles than antiparticles?
yeah, yeah, there all kind of physics is there. So one other interesting thing is when like when you don't have the collision between the lead nuclei, they just pass each other very closely, okay, without colliding. Uh, so So what happens is because see they are charged ions, they have basically uh, electric and magnetic fields, right?
Mm.
And in quantum sense they are emitting photons, they are radiating. So the photons from those two high energy moving nuclei, they interact, and the photons are such I mean they are such of such high energy that they can then get in, I mean interact, and they can form then quark pairs, and then you have jets coming from quarks. So jets are just bunch of hadrons, spray of hadrons. So you can study many interesting things, like people look for magnetic monopoles, and there is a called something called Britt-Wheeler processes, and there are many things are there. So yeah, it's a very interesting area also.
So, but photon interaction will produce uh, particles.
Yep, because they are at very high energy.
So but photons are constituent of
Yeah,
nothing. Right? I mean,
yeah. I mean, that is so. At high energy, you cannot think about it like that, right? Their electrons can annihilate and create quarks. Anything can happen, right?
so electrons can annihilate and create quarks.
Yeah, because if they have
But
enough energy, if they have enough kinetic energy, they can do it.
particles that are not cannot be broken down into further constituents can interact with each other and create said constituents.
Yeah, yeah. Electron positron can annihilate, right, and give you basically energy in terms of photons, and then they can create quarks. So these things
So,
happens.
so what about electron or photon? Two similar particles. Do they also produce like constituent upon interaction?
Electron, like electron. If you have electron and mm, no, electrons should have a positron to get annihilated, right?
No, no, not during annihilation. Like for example, you pointed out for lead, right? So
Mm-hmm.
if you pass them by closely, the
Oh, okay,
photons
okay,
that are
okay, okay.
being
You're saying electron collisions, like electron passing closely by electron. Yes, that's
no,
what.
no, like at very high energies, if we collide photon or electron,
Mm-hmm.
do they release
Quarks.
uh,
Yeah,
quarks or do
yeah,
they
yeah,
just
yeah. They
have an
can
impact?
release quarks. Yeah,
They can release quarks.
yeah. So that's what happens in this ultra peripheral collision, right? The one I was saying. So, photon from one nuclei interact with the photon from other nuclei, and they create quarks, basically.
So, sir, is it like is there is no way ki the quarks are coming from the photons themselves because
No, no, they are giving the energy into the fields, right? The quantum
the
fields.
fields are conforming into particles.
Exactly.
Uh,
So,
I read it in a book, sir. I think you might have heard of it, Six Easy Pieces by Richard Feynman.
yeah, I think I have read it long back.
So in that, it was given in a statement कि after a certain energy, the particles something along those lines, the particles blend into the field or something like that.
After some energy, the particles.
No, not the particles blend into the field, but the field can sort of become a particle after
Yeah,
a
that's what
certain amount.
happens. So all these particles are excitation of the field, right? The quantum excitations.
So,
So
sir,
that's why, I mean, when you study quantum field theory, these things will be very clear.
why can't we do some sort of similar thing with gravity then?
Gravity, how can you like study gravity like this? Because
No,
gra-
because if we want to know, like, okay, what is the quantum nature of gravity, then first we have to answer ki if it's quantizable like the other fields, no?
yeah, that's what people attempt in theory, right? There are some. So quantum gravity works in some different kind of space time geometries. called NT de Sitter space or something, ADS geometry. Do you know? Uh,
Yes, sir. I heard of ADCS geometry or something along those lines. There was a lecture on quantum black holes
yeah,
on
yeah.
YouTube from IISc.
So it's basically, it's basically like you have a toy model of things. So like in 11th 12th physics, when you have to solve something, like you imagine, imagine like there is a joke also, like uh, you know to some physicists were discussing, like uh, can you write a wave function of a cow or something. So one came up and said, let's imagine the cow to be a sphere or something like this. There's a joke, right? So it is like this, like we consider a space time in which the gravity can be quantized, and that turned out to be the anti-de Sitter space. So
So, but
which is,
that is again assumption, right? I mean,
yeah,
you,
this is a model, right?
so but it's not accurate to reality, right? Because
Yeah, it's not applicable to our universe, obviously.
so what's the use? I mean, we're just like trying to solve a question. For solving the question, for the sake of solving the question, we assume a
uh,
model.
yeah,
So
yeah, yeah. Like
how is that helpful?
that's what theorists do, right? They first try to model something, and then maybe they figure out what happens in reality, maybe some limitations. So right now we don't exactly know if our universe is flat or it curved at a higher, there are many things like we don't know yet. So, but people do, I mean, people play around and see what happens. So
It doesn't it make more sense for them to play around in with realities, this thing like parameters?
yeah, I mean, this is just a simple example. So
Mm.
I don't know what motivates them. You are going to a theorist, so you should know.
No, sorry, sir. I mean, if we assume ki okay, so gravitational field can be quantized, so let's try to answer some questions.
Hmm.
Then now it's just for convenience. We are now the questions that are being answered are out of sake of convenience.
Yeah, yeah, yeah.
Shouldn't it be going the opposite way from the answers that we have? We go back to whether gravitational field can be quantized or not.
Yeah, that is true. That is how. But yeah, these things are not that straightforward to think about. Like there are many constraints and things. So yeah, I mean, I don't concern myself with these things. So
Okay.
because yeah, first we have already have many things that we don't know, some many trivial things that we don't know about. So uh, first we have to figure out that, and then
So that's where the focus of theoretical physics should be, right? I mean,
yeah, yeah. But once again, like that I said, so everything that we can do, like standard model is complete, right? Everything. There are some questions about standard model that we don't understand. Like there are many free parameters that we put by hand inside the standard model.
yes, so also gravity has not been integrated into
Yeah,
the
yeah, yeah.
model. No?
Then there's dark matter and these things are there. So yeah, people are working. Let's see. But in my field, we don't concern too much. I mean, we don't focus too much on the standard model. Okay. Uh, so yeah, people are doing something related to that. Like you can study, uh, yeah, in heavy ion collisions, you can study about top quarks. So there are tagged jets coming from top quarks. So you can study about, because we have very high energy of in the center of mass, right? So you can easily produce top quarks, bottom quarks.
So any baryon or meson which has top quark as the constituent?
No, that's what I said, right? They cannot, they, they
So,
don't form any bond state.
so no bound state. So
Mhm.
so how do we just have a name
So,
for this
no, so
intermediate?
it decays, right? When it gets created, it decays into various particles, and then we reconstruct and we see that okay, something was there which decayed into this much of particles with this much energy. So that's how we know that its energy is this, and we call it uh, top quark.
So the top quark is a bound state itself, right?
No, no, no. It's a simple. It's a quark. It's
But then it decays into constituents.
not in constituents. It decay.
Then
It decays into other particles. So right now we discussed that in the beta decay, proton goes to neutron. So there the U quark decays into D quark or something, right?
yes,
So,
sir.
so it doesn't mean that the U quark has constituent, D quark has constituent, right? So it's all if you think in terms of energy and fields, then you will this will be clear. So top quark will give its energy to the field, and the field will then excite other particles. So that's what happens.
And we have only found one such quark like that.
And then what?
We have only found one such quark, like one such intermediate particle.
Yeah, yeah.
It makes it does it make sense that there should be multiple?
Wait. You were saying you mean from top quark we just get stable particles?
No. I'm asking if top quark is the only particle we have found that has such properties.
Yeah, in the quarks, it is the only one.
But does it make sense if there should be more like
Uh, like more quarks or what?
more quark or more fundamental particles like top quark?
Mm, there are some like these heavy mass resonances. Uh, so quarks are only six, right? There
Yeah,
cannot be more quarks. Okay, that is the standard model. I mean, this can be.
cannot be.
There cannot be, yeah.
But
There can be supersymmetric quarks, like which we have not observed yet. But the quark model is complete. I mean, so we have not found any particle other having quarks other than these six or five.
five, yeah. So the five are like fixed.
Mm-hmm.
So but the top quark is standing on the outside.
Mm-hmm. Yeah, that is true.
Okay. So there can be a possibility that such intermediate particles like the top quark are also there, right?
Yeah, there are many particles. So these higher resonances, cascade, and this D meson, yeah, these baryons. There are heavy baryons. They also decay very quickly. Okay, so we don't decay. We cannot detect them in the detector. We said detect the decayed products from them. So I mean, I think your question is how we differentiate from the particles coming from these baryons or resonances than from the top quark.
Yeah. Like I mean,
Hmm.
we have a top quark and it doesn't stay for long. It produces other particles
Yeah,
after
and
it.
then you have other heavy resonances like you may have rho meson, or you have baryon, cascade baryon, or something lambda. They also decay, right?
Yes. So like,
Hmm.
are they part of the same group or
No,
how do we
no, no,
just
no.
call
Yeah,
top quark a quark?
So this one, this is what, so this is what the achievement of experimental particle physics. So this is how we design our experiments and how we write our algorithms so that we can differentiate them. and there, I mean, many physics goes inside it, obviously. So, I mean, you can just read about. So Higgs, you know how Higgs was discovered, right? How we found the signal of Higgs. Higgs also is very, this formed for a very small fraction
Amount
of
of
time, and
yes.
then it decays into G boson or something. So,
Mm.
how did we find the signal of Higgs boson? So first of all, I mean, just the simple answer is we know the mass of Higgs from theory, like we know the mass of top quark from the theory. Okay.
Oh, so we observe a similar thing and we just say it is that
Yeah,
thing.
I mean it adds up to that. Like, so in case of Higgs, uh, we know the mass of Higgs, so we group bunch of particles and we see how much energy those particles have left in the detector, and then we adds up to them, and then we see that, oh, it's same as the mass of Higgs, so they must be coming from Higgs, right?
Hmm.
And then we find more such groups of particles, and we see that, okay, and then I mean, doing, I mean, looking at 100 events, you cannot say I mean, you cannot confirm that Higgs exists, because there can be, I mean, randomly there can be randomly, if you select some particles, you will get mass equal to Higgs, right? Energy that is equal to mass of Higgs.
Yeah.
But if you see the same pattern for billions of events, then you can confirm, oh, okay, so it's not a statistical fluke. What we are looking at is a real thing. So there, there what statistics helps us. And so this is how we do these experiments, and we discover rare particles like this. And so also there are so for Higgs there will be other particles which will give, same amount of, I mean, same particles which were equal to the mass of the Higgs, so we consider them as background, and since they are mixed with other particles, so I mean, it's a very interesting thing to separate yours, what you are interested in, what we call signal, so signal of Higgs, and the background, which is other particles which give the same kind of particles, decade daughters. And so people use various techniques, so machine learning is right now being used. So for Higgs, they use a machine learning technique called BDT, boosted decision tree. Do you know about it?
No, sir.
Yeah. So right now people are using, these neural networks and things like that. So it's a very interesting field. You can read about it more. Okay. So yeah, do you have anything to ask?
Yes, sir. I was just I just remembered that in the lecture of the Dr. Polisso's lecture, in that when he was describing elementary particles for the Higgs boson, he had written ki we have found a suitable candidate for Higgs boson.
Hmm.
So that just kind of threw me off because like I thought ki Higgs boson has always been there. I mean,
Yeah,
found.
but the lecture was like, I think, when was the lecture? Yeah, I mean, that time it was new, so maybe that's why he told it. But now we know that what we measured was Higgs boson, because various following that paper, there they did many more checks, and they cross checks, so to make sure that, yeah, whatever we discovered was the Higgs boson. So now it is confirmed that we discovered it. There is no ambiguity in that.
So the Higgs boson gives mass to the particles, right? So it's part of the Higgs boson field, right?
Mm, yeah, so there is a field, and then, like I said, the quantum excitations are Higgs bosons.
So does the Higgs boson interact with the gravitational field?
Yeah, that we don't know. because standard model we don't consider the gravity, right? So I don't
Oh,
know.
okay. So this is where the, like sort of gets like confusing, like why they are not doing that.
Mm-hmm. So yeah, I mean the picture is like this. So Higgs boson provide mass to elementary particles, and then gravity act on them.
So that I
Right.
mean, because if Higgs does interact with gravitational field, depending on the nature of their interaction, we can say ki if Higgs is responsible for giving an messenger particle between the graviton,
Mm-hmm.
can it give the mass to that? And depending on the nature of interactions, we can sort of deduce, right, ki if there is a contribution of mass to the graviton, which will
Hmm.
sort of show ki if graviton exists or not.
Yeah, I mean, but the gravitational field that you are talking about and the Higgs field that you are talking about, these are two very different fields. So the gravitational field is a, it's not a quantum field. Uh, so you're talking about the quantum gravitational field or what?
Yeah, quantum gravitational field. I mean, if
Yeah, yeah. Okay, so whose excitations will be graviton, and then you have Higgs field, right?
yes, no, here like I'm not assuming ki the graviton does exist.
Okay.
The only thing we know for sure about gravity is like there's a gravitational field.
Yeah, but gra- we don't know if the gravitational field is quantized in our universe.
Yes, so depending on how the gravitational field interacts with the Higgs field or the Higgs boson, we can sort of say, right, ki if it's quantized or not.
Mm,
If there is a similar interaction between the Higgs and the
but yeah,
gravitational
but
field,
how will you find a signal? Like there cannot be a ex- uh, how can you test this? There is no way you can test this, right?
so
I don't know. I have not thought about it.
maybe black, like that's why I think black holes are like should be studied extensively,
Yeah, but
because that's the only environment in which we can have the energy required for the Higgs to form in a gravitational field that is very strong, such that uh, all sorts of interactions can occur.
yeah, that is interesting. Uh, then this goes into the field of astrophysics, astroparticle physics kind of thing.
So,
Yeah.
uh, those things are kind of interesting. I think I would like to. I mean, I would like to think because I like the study of black holes and all personally. So I think that if we figure that thing out, then we have figured out everything.
Yeah, yeah, that is true. That is true. But again, like, see, these ideas are fine, but so to bring these ideas into, into some framework that you have to, I mean, that you have to talk to people and see if that is feasible or not. But yeah, I mean, thinking about these things is great. So yeah, should you should get contact. I mean, get in contact with some good theorists and then present your ideas and see what they say, right?
Yes, sir. But I thought of I'll just have a review paper under my name so that I don't like
Mm-hmm.
go completely empty-handed in front of
Yeah,
them.
yeah, yeah, no, no, that is a good idea. Yeah.
'Cause then I'll feel like I feel like I'll kind of look stupid, like just um,
Yeah, yeah, yeah,
quoting.
yeah, I see. No, it happens. Yeah, people do form prejudice and things like that.
Yes, also I'm from a BTech of aerospace engineering, so it's not very.
Mm, yeah, I understand. But yeah, let's see.
Yes, sir.
Okay, so yeah, all the best.
Thank you, sir. Thank you.
Yeah. So I think it's almost time. We did a very long discussion. It's fine. Uh, so Okay, we will meet again. And if you have something else to ask, you can ask. And, okay?
Done, sir.
Yeah. Okay. Then let's close this session today. Okay,
Yes, sir.
bye.
Bye, sir. Bye, sir.
Bye.